Have you ever wondered how we build an AI that's actually smart and not just, a really good parrot that memorizes everything? Well, it's this incredible balancing act, kind of like a high wire walk between learning a real pattern and just cramming for the test. Today, we're going to pull back the curtain and see how engineers tame the wild complexity of their models to get that balance just right. This right here, this is the core question. Think about it like this. If you're teaching a student, you don't want them to just memorize the answers to last year's exam, right? No, you want them to understand the principles behind it all. It's the exact same goal for AI. We want it to grasp the underlying rules so it can handle stuff it's never seen before. And this ability is what we call generalization. It's everything. The model has to be able to look at brand new data and make smart predictions. It needs to separate the signal, the true underlying pattern, from all the random, chaotic noise that's just part of any real-world dataset. Honestly, that's the holy grail in machine learning. So, to get to that holy grail, we first have to understand the two big things that try to stop us: bias and variance. These are the two fundamental enemies of generalization. Pretty much every mistake a model makes can be chalked up to one of these two, so getting a handle on them is absolutely step one. So first up, we have bias. Think of bias as stubbornness. A high bias model is just too simple for the job. It has these rigid, overly simplistic assumptions about the world, and it just can't see the complex patterns in the data. We call this underfitting. It's kind of like trying to trace a beautiful, complex curve using only a short, straight ruler. You're just going to miss the point entirely. Now, on the complete other end of the spectrum, you've got variance. This is the error you get from a model that's too flexible, too jittery. A high variance model doesn't just learn the pattern, it learns every single random quirk and bit of noise in the training data. This is overfitting. This model absolutely aces the practice test, but then completely bombs the final exam because it memorized noise like it was gospel. And this leads us to the classic challenge, the bias-variance trade-off. It's this constant push and pull. If you try to make your model simpler to lower its variance, you almost always increase its bias. And if you make it more complex to crush that bias, you risk jacking up the variance. The art and science of this whole thing is finding that perfect sweet spot right in the middle, where the total error is as low as it can be. Okay, so that's the million-dollar question, isn't it? How do we know what's wrong with our model? Is it being too simple and stubborn, or is it being too complex and flighty? Luckily, we don't have to just guess. We have some really cool diagnostic tools that let us look inside and see what's going on. And our number one tool for this is the learning curve. Basically, we plot the model's error on the data it trained on, and then we plot its error on a fresh set of data it's never seen before, the validation set. If both errors are high and stuck together, that's high bias. The model just isn't learning. But what if there's a huge gap? The training error is super low, but the validation error is way up high. That is the classic fingerprint of high variance. The model is overfitting. All right, so we've run our diagnostics, and let's say we've found the problem. A lot of the time, that problem is high variance. Our model is overfitting. So what do? Well, it's time to open up the Regularization Toolkit. This is our collection of techniques designed specifically to rein in that complexity. So what is regularization? At its core, it's basically a penalty system. It's our way of telling the model, hey, I need you to learn the patterns in this data, but I'm also going to penalize you if your solution gets too complicated. This gently nudges the model towards finding simpler, smoother solutions that are way more likely to generalize well to new data. Let's look at the two big ones in the toolkit. First, you've got L1, also called lasso. It adds a penalty based on the absolute value of the model's parameters. And its coolest trick is that it can shrink the parameters of useless features all the way down to 0, basically acting like an automatic feature selector. Then there's L2, or ridge. It penalizes the squared value. This guy pushes all the parameters towards 0, but doesn't usually zero them out completely. It's fantastic when you think most of your features are probably useful to some degree. Now, in the world of giant neural networks, we've got another amazing technique called dropout. It's a wild idea. While the model is training, at every single step, you just randomly switch off a bunch of its neurons. Just gone for a second. This sounds crazy, but it forces the remaining neurons to learn to be more robust and not rely too much on any one of their neighbors. It's like training a basketball team by randomly making players sit out for a few minutes at a time. It makes everyone else a stronger, more versatile player. And the toolkit is deep. We have other brilliant, almost common sense ideas, like early stopping. which is literally just watching your model's performance on new data and hitting the brakes the second it starts to get worse. Or data augmentation, where we just create more training data by, say, flipping, rotating, or tweaking the images we already have. They're all super powerful ways to fight off overfitting. Okay, so everything we've just talked about, that's been the bedrock of machine learning theory for a long time. But in the last few years, especially with these huge deep learning models, something really, really weird started to happen. It turns out the old rulebook doesn't always tell the whole story. So remember that classic bias-variance trade-off? It gave us this really clean, intuitive U-shaped curve. As you make a model more complex, its error goes down, 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 until it hits a sweet spot. Then, if you make it even more complex, it starts to overfit, and the error goes right back up. Simple enough, right? But what about the models we're building today? We're talking about neural networks with billions of parameters. That's way more parameters than data points they're training on. According to that classic U-shaped curve, these things should be an absolute, unmitigated overfitting disaster. But they're not. So what on earth is going on? And here is the big reveal, the plot twist. Researchers discovered something called the double descent phenomenon. They found that, yeah, the error curve goes down, and then it goes back up, just like the classic theory predicts. But if you just keep pushing, if you make the model even more absurdly complex, past that overfitting peak, the error can start to go down again. That U-shape was only the first half of the story. It's incredible. This discovery just completely broke people's brains for a little while. How is it possible that a model that has perfectly memorized the training data can somehow get better at generalizing? The answer isn't in the model architecture itself, but in how we train it. It's like there's a hidden hand in the algorithm guiding the way. This idea has a name: implicit regularization. It turns out that the algorithms we use to train these massive models, like stochastic gradient descent, or SGD, have a secret of their own. When there are zillions of different ways for a model to perfectly fit the training data, these algorithms have a built-in preference. They are biased towards finding the simpler, smoother solutions, which just so happen to be the ones that generalize better. So this is the really profound insight here. The training process itself, the journey, not just the destination, is acting as its own powerful form of regularization. That slightly chaotic, bumpy process of training a model on small batches of data actually keeps it from settling into a weird, jagged, overfitted solution. It naturally nudges it towards a better answer, without us even having to explicitly tell it to. And this has totally shifted how we think about building AI. The modern playbook isn't about finding that one perfect sweet spot of complexity anymore. Often, it's about going big, using a huge over-parameterized model, and then applying strong regularization, trusting that both our explicit tools and the implicit magic of the training algorithm will guide it to a fantastic result. Which, really, it just leaves you with this fascinating thought to chew on. We're finding out that the tools we've been using for years have these incredible beneficial side effects that we never even designed on purpose. It really makes you wonder, doesn't it? If our algorithms have these hidden powers, what other secrets is AI hiding from us? Right there in plain sight, just waiting to be discovered.